Hello students, welcome to Chapter 2 Atoms Lecture Video Part 3. This is our final or the last video for this chapter. This video will conclude the chapter and we will learn about the concept of mole and how it is used. We will also learn about Avogadro's number. There will be problem solving where we will learn to convert between mass of a substance and moles of the substance. We will also learn a little bit about how elements are arranged in the periodic table, and then we will conclude by distinguishing between atoms and the molecules. So let's begin. So let's start with learning about the mole. And if you remember, this is the same mole that we looked at the 7 SI base units and in chapter 1. And if you remember, I said mole is something that is used by chemists to measure the amount of a substance. So let's define what a mole is. A mole is the number of atoms in 12.011 grams of carbon 12. It's a carbon element on the periodic table. And the number is 6.022 times 10 to the power of 23 atoms. And this number is also referred to as Avogadro's number, named after the person who did the calculations to find this number here. So all of you should know what the Avogadro's number is, which is 6.022 times 10 to the power of 23. So how do chemists use this? So a good analogy that we can think that I can think of here is see how everyone knows that a dozen corresponds to 12. So I could say I have a dozen pencils, and you will know I'm talking about 12 pencils. Or a farmer might be selling the eggs or bananas, and he'll say, I have so many dozen or 1 dozen of eggs. So we understand the number is 12. Similarly, whenever we talk about the Avogadro's number, we know that 1 mole corresponds to 6.022 times 10 to the 23 atoms. So now we come to a point where where we can ask a question like how much does a mole of 6.022 atoms times 10 to the 23 atoms or molecules weigh? And the answer to that depends on the element or the elements. And we always measure it relative to carbon 12 in the periodic table. So 1 mole or 6.022 times 10 to the 23 atoms of pure carbon 12 isotope has a mass of exactly 12 grams, and therefore the molar mass of carbon 12, so the molar mass of carbon is then 12 grams per mole, because there are so many per mole. So what's molar mass then? So the mass in grams of 1 mole of a substance is known as molar mass. And this value is the sum of atomic masses of the elements in the compound. Like for 1 carbon atom, it was C12. So let's look at the compound or the common molecule that you have been looking at, which is water. So H2O. So hydrogen, in water molecule, there are 2 hydrogens and 1 oxygen. So you will look at the periodic table and you will see that the atomic mass of hydrogen is 1. So it will be 2 times 1 plus The atomic mass of oxygen is 16. So 2 plus 16 is equal to 18. So 18 grams per mole, or 18 grams in 1 mole. It will be the molar mass of water molecules. So we can say that there are 18 grams of water molecules per mole of water. So this figure here is connecting the mass, two moles, two molecules, and let's look at it. How is it connecting? So you look at the mass of element or compound. So if you know the molar mass, and what is the unit of molar mass, we just saw it in earlier slide. So it's gram per mole. And if you remember, the mass, the unit of mass could be grams in this case. So if you have grams and you know the grams per mole, which you can calculate because you know the mass of the elements from the periodic table, right? So you can calculate the molar mass, and we can arrive at, so this could be our conversion factor, and we could arrive at the moles. And now if you want to find out the number of atoms or molecules, we can use Avogadro's number. So Avogadro's number was 6.022 times 10 to the power of 23 units, and that could be number of atoms or molecules. And if we go to the solution, it will be ions, but for now we can just stick to the atoms and molecules. So once you have, because we know that 1 mole is equal to Avogadro's number of atoms or molecules, so we can go from moles to moles to number of atoms or molecules, or vice versa, and that's why you see the double arrow here. You can go back and forth by using Avogadro's number as a conversion factor. And here also you could go from mass to moles or moles to mass by using the molar mass. Now I just want to quickly review that whenever we have an equality, and in this case the first equality is 1 mole is equal to 6.022 times 10 to the 23. So depending on what do we want to find out, we can use the conversion factor, right? So if you're going from, say you're going from moles to number of atoms, to the number of atoms, so what we do is we just place the atoms on top and 1 mole at the base. So 1 mole has Avogadro's number of atoms. So 6.022 times 10 to the 23. So what happens is you can cancel moles to moles and you're left with atoms here, and that's what we wanted to find out. Similarly, you can use the same concept, like if you want to go from moles to grams, you can use grams per mole as a conversion factor, or if you want to go from grams to moles, then you can just flip this and use it as 1 mole has that many grams of a substance, and we will apply this in the problem solving, so it will make more sense. and you'll get a practice out of it. So let's look at a problem solving strategy using mass ratios. So here's a problem which says hydrogen gas for fuel cells can be made by decomposing methane, which is CH4, and is a natural main component of the natural gas. And this is a general statement. So let's look at the main part of the problem, which is saying the decomposition gives carbon and hydrogen in the ratio of 3 parts by mass of carbon to 1 part by mass of hydrogen. And this is important thing because we are talking about the mass ratios. And the final, what it wants us to solve is how much hydrogen can be made from 90 grams of methane. So here's a problem where we will apply the mass ratio. So the decomposition is happening like this. Methane, which is CH4, is giving you carbon and hydrogen. So 1 carbon and 4 hydrogen. So let me just quickly write it. CH4 will decompose to give you carbon plus 4 hydrogen. Just looking at the formula, right? There is 1 carbon atom on both the sides and 4 hydrogens on both the sides. So if we look at the formula, we know that for each carbon there are 4 hydrogens, right? We can express that a ratio in the form of 1:4. So there is 1 gram of hydrogen in 4 grams of methane, which is CH4. 3 parts and 1 part. Okay, now let's look at the solution then. So we start with the given quantity here, which was 90 grams of methane, and the problem wants us to find the mass of hydrogen. So because we are finding grams of hydrogen, we want to keep it on the top. So 1 gram of hydrogen divided by the 4 grams of methane. So the grams of methane and grams of methane will get cancelled, and you will be left with 90 times 1 divided by 4, which will be 22.5 grams of hydrogen. So that's the number with the 3 significant figures, and grams is the unit. So this is how we use the mass ratios to find the grams of either substances. Now, if it was some other unit like carbon, then we would have used a different ratio. Now I want you to do some problem solving based on moles to mass and mass to moles of a substance, and want you to get comfortable with this concept because this is like our foundation for these type of calculations, and in the following chapters in the course more building blocks will be added to this foundation. So let's get started. So here the problem number 1 is how many moles of carbon dioxide are represented by 150 grams of carbon dioxide. So simple. The grams of CO2 is given to you. So mass, this is the mass of carbon dioxide, and it's asking you to find out the moles. So you know the conversion is from mass to moles of a substance. Okay, and what is the connection between mass of a compound and the moles of the compound? So if you remember the figure where I had shown you the 3 blocks connected by mass, molar mass, or Avogadro's number, that is what will be used here. whenever I show you the problems, make sure that you pause the video and think about it. Um, Try to collect what is given, what we need to find out, and what information do we know, and then solve it. Um, and after a while, you play the video again and look for the solution that's explained to you. So, how many moles of carbon dioxide then? So, we will use the molar mass of carbon dioxide, molar mass of carbon dioxide. And how will we calculate that? So, how many atoms of carbon? So, one carbon, and how many oxygens? So, this subscript here 2 is telling you that there are 2 oxygens in the molecule. So where will you get those numbers? You will look at the periodic table and find out the the grams of carbon per mole. So this is, or the molar mass. So the 12 grams of carbon plus 2 times 16 in this case. Sometimes you will say 15.999, something like that. So 12 plus 2 times 16 should correspond to 44 grams of carbon dioxide in 1 mole of carbon dioxide. So we have figured out the connection. Now we want to start with the grams. Use this conversion factor to get to the moles of carbon dioxide. So what do we need on the top? Because we are starting with the grams and we want to arrive at the moles, we want to have moles on the top. So we will say 1 mole of carbon dioxide has or corresponds to 44 grams of CO2. So 150 grams of CO2 is given to you, 150.0 grams of CO2. So grams of CO2 and grams of CO2 get cancelled and you're left with moles of carbon dioxide. So you will do the calculations, 150 divided by 44, and the answer, and do the final answer. So let me pause the video and check the answer. So it is coming out to be 3.409, but notice there are only, notice the significant figures. So you can say 3.41 moles of carbon dioxide. So in similar way, you will solve the second problem. So the second problem is, what is the mass in grams of 3.25 moles of ammonia? So what's happening here? We have a different molecule which is NH3. So you will find the molar mass of NH3, which will be 1 nitrogen atom plus 3 hydrogen. So find the molar mass of ammonia, and this time the moles are given to you. So you will start with moles. So 3.25 moles of ammonia, and you need to find the grams of NH3. So what should happen here? What will you do to your molar mass? So because you want grams of ammonia, so you'll say, you will find out. So the grams will be on top. So 1 mole of ammonia has how many grams of ammonia? So nitrogen. So you will look at the periodic table and look at the mass of nitrogen. So nitrogen is 14, and there are 3 hydrogens. So 14, 15, 16, 17. So you will have 17 grams of ammonia in 1 mole. So moles of ammonia and moles of ammonia will get cancelled, and you will multiply 3.25 moles with 17, and you will be left with the final answer, which should be around 55.25 grams of ammonia. Let's just check that answer. So yeah, the answer is 55.25 grams of ammonia. So please practice the problems like the ones that I showed you in an earlier slide, and everyone must know how to go from moles to mass or mass to moles conversions. You will be tested on this concept in the exam. So please practice that. And now we are going to switch gears towards learning about periodic table and how the periodic table was formed. So I'm going to describe how the elements were arranged in the periodic table, and how did the periodic table come to reality. So it was Dmitry Mendeleev, the Russian chemist, which is his picture is shown here. Um, he he was a well-known scientist, and he was discovering new elements were getting discovered at that time, and he could not find anything where all this information about the elements was organized. So he arranged then known 63 elements into a periodic table, and he wrote his own textbook with this table. So that's how it all started. So out of chaos came the periodic table. He organized all that data, and then he also studied the nature and the origin of petroleum, and he made many other contributions to the science. And Mendeleev has has an element in the periodic table, element 101, which is named Mendeleevium, MD, in his honor. So I would like you to open a periodic table in your textbook and figure out where is it, and let me know if you could find the element 101. So as these elements were being discovered around 1800s and before that, what Mendeleev did was he linked the chemical properties to the atomic masses and developed the periodic law. So he also published this table. And the cool thing about his prediction was he could even predict the properties of the elements that were not yet discovered. So he left some blanks for the elements and predicted the properties, and I will show you that in the next slide. So this is the picture. This is a picture of the periodic table that Mendeleev and another scientist actually worked on it, but main credit goes to Dmitry Mendeleev, and he arranged these 63 known elements in the order of increasing atomic mass. This has changed now. Now the elements are arranged with increasing atomic number, and we will study that in the chapter 3. But for now, this is how the periodic table looked like, and he left the gaps for the undiscovered elements, and he also predicted the properties of those undiscovered elements. And the nice thing about it is, when those elements were eventually discovered years later, many of his predictions were accurate, and I will show you a table where I'll show you the properties of the elements, at the comparison of what he had predicted and what was observed. So why is the periodic table of elements called periodic table? Because periodic here means that something is occurring at regular interval. So the physical and the chemical properties of the elements are periodic, and that is the reason why these elements are arranged in a given column because of these similar properties. And we will study that in detail in next chapter that's coming up. However, this is I want to bring your attention to the slide, the current slide. So here in the orange colored figure here, you see how an element is represented in the periodic table. So you have Fe, which is the chemical symbol for iron. Then you have atomic number, usually represented by letter Z on the top. And then you have atomic mass, which is the weighted average of all the naturally occurring isotopes. This is how you will see the elements represented in the periodic table. And table 2.2 here tells you the properties of germanium predicted by Mendeleev versus what was observed when they were discovered. So let's look at the first property, which was atomic mass. So Mendeleev predicted it and called it Eka silicon because it was in the same column as silicon, and he had left a blank spot for it to be filled. So he predicted the mass will be atomic mass will be 72, and when it was observed, it was found to be 72.6. So he predicted it in 1871, and in 1886 it was found to be 72.6. Here, the predicted density was 5.5 grams per cubic centimeters, and observed was 5.47. So that's pretty close. Look at the color. It was predicted to be dirty gray, and it was observed to be grayish white. So pretty similar. And then he also predicted the density of oxides, which was 4.7. And very close to what was observed. And the boiling point of the chlorides of this element, he said, would be below 100 degrees. And look here, it is around 86 degrees Celsius. So the predictions were really good. And this is all that we will study for now at the periodic table, but I would really like you to see a periodic table today and count how many groups are present, how many rows are there. So there should be 7 rows and 18 groups there, and we will revisit the periodic table in the coming chapter. So we are almost at the end of the chapter, and here we see how real and relevant is the concept of atoms, and we can see a image of a manganese atom actually in the picture here. So this is a computer enhanced image of the atom, and the image is actually taken by something called as scanning tunneling microscopy. Short form is STM. So you could actually see the atoms of manganese. The element is manganese, represented by Mn, a symbol Mn in the periodic table. So we see here that atoms are pretty real, and they are highly useful. It's a highly useful concept which the scientists today use. So let's look at now that we have covered the chapter and we are almost at the end. Let's quickly review or know the difference between atoms and molecules. So we know what is an atom. Atom is a tiny particle of a tiniest particle of the matter, and the molecules are actually the group of atoms which are chemically bonded or connected to each other. So more than two atoms form a molecule. Atom is represented by the symbol of the element. So for example, hydrogen here is hydrogen H is the symbol for hydrogen element, or that it represents one hydrogen atom, whereas H2 or molecules are represented by using the chemical formula. So whenever you will see H2, that is the formula for the molecule of hydrogen. So it's made up of two hydrogen atoms. So let's pause the video and think about any other atoms or molecules that you remember. So any atom will be represented as the symbol for that element. So for example, carbon atom will be represented as C. Iron was represented as Fe. So these are some of the examples. Whereas molecules, you could have a water molecule, H2O, which will be made up of two hydrogen and one oxygen atoms. Or you could have carbon dioxide. So one carbon and two oxygen atoms. So that's the chemical formula for the molecule of carbon dioxide, or the chemical formula for water. So you see groups of atoms connected to each other forms the molecules. So on this slide, we will see the application of green chemistry, and see how it is used. So green chemistry means replacing rare or hazardous substances from more abundant or less hazardous substances. So you want to reduce any hazardous substance in the environment. So new technologies have led to, one such example is new technologies have led to the formation of mercury-free efficient light bulbs. And here you see this liquid mercury-free bulb. So this is an example of green chemistry technology, which replaced the earlier fluorescent bulbs which used to contain mercury by these mercury-free light bulbs. So you're reducing the toxic element and thus contributing to the green chemistry and to the environment. So here's an example of that. And with this, we wrap up chapter 2.